All right, we're going to take a whirlwind tour through all of the formulas in this unit and comment on where they come from and where they go. Cotton Eye Joe. We started with recognizing that for a circular orbit, the centripetal force is equal to the gravitational force. So we started out by saying centripetal equals gravitational force. So keep in mind, we're talking about forces and only circular forces, circular motion. And that allowed us to equate those two formulas, cancel some stuff out, and realize that for a circular orbit, the velocity of the orbiting body is going to be equal to g big M, that would be the mass of the sun, for example, over the r, where that would be the distance away from the center of the sun. So the velocity of, say, Earth would be equal to g times the mass of the sun divided by the radius of the distance from the Earth to the sun. So I put a yellow star next to that because that's kind of an important one. And basically, one of the big ideas of all the formulas in this unit is several of them are derived from things that we are more or less familiar with, and a couple kind of came out from new ideas. So far, we just substituted and realized essentially a new formula that can apply to planetary motion. Then, again, continuing on this circular motion idea, realizing that velocity is a distance divided by time, and that distance for a circular path would be the circumference, and the time would be the period. 2 pi r divided by the period would give 4 pi squared r squared over t squared. So there's your velocity squared equals big G, so there's your velocity squared, big G times m over r, and we move a few things around, and we come up with r cubed equals big G, big M, mass of the sun, divided by 4 pi squared, all parentheses, because that is a constant for any planet, the big G and the mass of the sun over 4 pi squared, times t squared. So we essentially are revealing this r cubed is proportional to t squared for any planet in a particular solar system. If you're talking about our solar system, the only variable in question would be the mass of the sun. The r cubed to t squared relationship is going to be constant. Basically, it's going to be the same for every planet. And at first, we got here using circular orbits. But for reasons we're not going to delve into, we can also apply this to elliptical orbits where we need to consider the r as the semi-major axis. So the semi-major axis is the distance as indicated here. You got an ellipse. If you take the entire distance of the long axis and cut that in half, that is the semi-half major long axis, the semi-major axis. The semi-major axis can be used in this relationship. So that's convenient. So it's an extension of what previously was exclusive to circular motion, can now also be applied to elliptical orbits. All right, so far that's sort of a summary of how forces and circular motion got us some stuff that was useful. Then another big piece of this is energy. There are a million YouTube derivations of this formula, so I'm not going to do it here, but we determined that the potential energy of a planet in some radial orbit has an energy of negative big G, big M, mass of the sun, times the small m, the mass of the orbiting body, divided by the orbital radius. And basically, that essentially is giving us a new expression for potential energy. Previously, we've been using MGH, but for orbitals, orbital radius, big bodies going around in space, this is our new expression, which fits neatly into the conservation of energy, which we're all very familiar with. So kinetic energy plus potential energy at one point equals kinetic plus potential at another point. The only change we're making here is we're inputting this new expression for potential energy, but otherwise it fits into this framework that we are very familiar with. So I got a yellow star next to that because that can be applied to any uh, orbit, circular or elliptical. It would make sense that would be for any orbit because with an elliptical orbit, you're going to have a different radius at different places, and as a result, you're going to have different speeds there. So you're going to have a trade-off between potential and kinetic energy as you go closer and further. However, we can consider the special case where the orbit is circular. If the orbit is circular, then the radius doesn't change, which means the potential energy doesn't change, which also means the velocity and kinetic energy won't change. So let's try a substitution. From above, we recognize that for a circular orbit, v squared equals big G, big M over R. So let's sub that into the kinetic energy equation here and recognize that those two energies simply added together combined equal the total energy of that body in orbit. So with that substitution, we sub in for v squared, we do some canceling, and it reveals that the total energy of a body in circular orbit exclusively is equal to negative 1/2 big G, big M, little m over R. And lastly, our new idea is Kepler's laws. A lot of what Kepler has to say is largely conceptual, just recognition of sort of geometrical occurrences, but not a whole lot that we can actually make a calculation with. One is that recognizing that the orbit of a satellite is an ellipse with the sun at one of the foci. So we've got the sun is here, and an imaginary point out in space is the other focus, and the shape is an ellipse, as Mr. Mahaka described earlier. One kind of interesting feature about the movement of planets around the sun is that they'll sweep out equal areas in equal times. As a planet starts from far away and travels inward towards the sun, it's going to pick up speed. And so by the time it gets to a position close to the sun, it's going to cover quite a long distance because its linear speed is great. So in a certain amount of time, it's going to sweep out this area. And as it gets further away, it's going to slow down. And so its linear speed here is going to be relatively slow. So it's going to sweep out not a great distance linearly, but because it's so far away, that area inside there is still going to be equal to the area it swept out when it was closer to the sun. So that's an interesting artifact of gravity and elliptical orbits. And the last law is that the radius cubed is proportional to the t squared, to the period squared, is true for all planets. So that's to say that the r cubed over t squared ratio for the Earth is equal to that of Mars, is equal to that of Jupiter. So that particular ratio is equal for every planet that orbits a given star. And so this essentially is a summary of all the formulas in this unit, and just wanted to provide this as kind of a one-stop shop without a whole lot of background. But if you wanted to remember how and when and where a formula might apply, I'm hoping this will be useful. And I almost forgot one thing, and that pertains also to elliptical orbits. Well, I suppose it pertains to circular orbits, but it's more useful in elliptical orbits, and that is conservation of angular momentum. And that is in reference to, say, when we've got an object moving in a straight line around or is about to move around an object at some radius. And this is where our perpendicular becomes a useful concept, because when we're talking about traveling in an ellipse, there aren't many locations where the object's velocity is actually perpendicular to the radius, except for two very useful points in particular, and that is the perihelion, and that is, let's say it's going around this way. At this moment, its velocity is this direction, and its radius is like that. The perihelial radius, I'm making that up, are at 90 degrees, and also at the aphelion. And at that moment, the velocity and radius are at 90 degrees. And so, given that the angular momentum is mvr for a straight line moving object, then we could say that mvr at its perihelion is going to be equal to mvr at its aphelion. And since it's the same mass in both questions, I guess we could put all the subscripts in. The velocity times radius at perihelion is going to be equal to velocity times radius at aphelion, and it makes an easy way to determine the speed at one or the other if you know all the other things.